Alright, in this video we'll be looking at inductance and how that relates to inductors, okay? So before we get into any of that, we need to have an idea of what Lenz's law is. Lenz's law states that an induced EMF will be in the direction to oppose the change that caused it. And so by extension, because the induced EMF will be in opposite direction to the change that caused it, we can also say the induced current, because the direction of the EMF will determine the direction of the current flow, okay? And so what Lenz's law is essentially saying is that if we have a coil over here, okay, like so, and then we can apply an amp meter right over here so we can measure the current, and we were to have a bar magnet with a north pole here and a south pole here, and if we were to push this bar magnet through the coil, okay, as we know for our bar magnet, we're going to have magnetic field lines coming out of it like so, okay? And so as the bar magnet goes through, these flux lines are going to interfere with the coil, okay? And from my video of Faraday's law, we know that when magnetic field lines cut through a coil, we're going to have an induced EMF, okay? And we know our equation of Faraday's law is negative N change in flux all over change in time, okay? And like I said in my Faraday's law video, this negative implies Lenz's law, okay? And so what this negative again tells us is that when this bar magnet goes through, but this EMF is going to be in opposite direction to the change that caused it, okay? And so when we produce an EMF in the opposite direction, we're obviously going to produce a current in the opposing direction. And what this is going to cause in the coil is an electromagnet to be formed, okay? And when the electromagnet is formed, what this is going to do is it's going to produce a north pole here and a south pole here, okay? And again, as you can tell, it's going to oppose the bar magnet from going through, right? Because we have a north pole here and a north pole here. And the exact same thing in the opposite direction happens when we pull out a bar magnet, okay? Let's say we have a bar magnet within the coil, okay? And we pull it out, okay? And now we have our north pole here and our south pole here, and we're pulling it outwards. This is again going to cause a change in flux, and therefore Faraday's law applies. And in this case, it's going to be a south pole here and a north pole here. Thus, this electromagnet is going to pull the bar magnet back in, okay? And so this knowledge leads us to the component of inductors, okay? So this is a electrical component, all right? And this component resists changes in current, okay? And essentially, an inductor is a coil of wire, okay? Just like how we have a coil of wire here, okay? And the symbol for it we can denote as something like this, okay? And if we see a bar on the top of that coil, that just means we have an iron core within the coil. And what an iron core does, it just makes the electromagnet even stronger, okay? And therefore making the inductor even stronger. If we were to have a circuit like so, okay, we're going to have a switch over here, and then we're going to have our inductor over here like so. Okay, so right now we have zero current flowing through the circuit because we have the switch open, okay? But if we were to close the switch and therefore make our switch in this position right here, current is obviously going to start to flow throughout the circuit. So like I said over here, an inductor resists changes in current, okay? So our current went from 0 to max, and so obviously there is a change in current there, okay? So how does this coil resist the change in current? And so what the inductor is going to do, it's going to simulate an opposing EMF, okay? And so we can sort of replace this inductor with a source of EMF that goes in opposite direction to the source EMF, okay? Okay, and so what we can say is that initially, the inductor is going to oppose oncoming current, and it does this via what's called a back EMF, okay? That's what we call our opposing EMF right here, okay? A back EMF is going to be produced, which is just an EMF that opposes the source EMF, which therefore restricts the flow of current, okay? So the current is not going to be max initially. However, after some time, the inductor will allow max current to flow. The reason for this is because the inductor resists changes in current, okay? So if the current has been trying to flow for some time, there has not been a change in the current. And so therefore the inductor will no longer cause resistance because there has been no change. And so eventually, after some time, inductor allows current to flow at the max current, okay, I max. And essentially, it just acts as an ideal wire, okay? And this obviously makes sense because we know that the inductor is just a coil of wire, okay? So if there's no resistance, then the current just goes through the coil like an ideal wire, okay? And so inductors have a property which we can call inductance, okay? And so our inductance is a measure of how well an inductor is at creating a back EMF that opposes oncoming current. And so therefore, the higher the inductance of an inductor, the better the inductor is at producing a back EMF to oppose oncoming current, okay? And so the formula for this is our back EMF is equal to minus L, which is our inductance, okay, so that's our inductance property, multiplied by the change in current all over the change in time, okay? So this is our EMF, okay? So that's the EMF produced, that's the back EMF produced. This is our minus sign, and that's due to Lenz's law, okay? And so this is what tells us that it's a back EMF. This right here is our inductance, which I just said, and that tells us how good the inductor is at producing that back EMF, okay? And the inductance is measured in what's called henries, okay? And this has a symbol of H, okay? And this is obviously the change in current, which obviously has a unit of amps, and this is the change in time, which even more obviously has a unit of seconds, okay? So we can see how this applies to a circuit. Let's say we have our circuit right here, and we have an inductor over here, and then we can have a iron core if we want. We have a resistor, and we will have a switch like so. We can say that this is a 12-volt battery, and we can say that this has an inductance of 0.6 henries, and we can say this resistor has 2.4 ohms of resistance, okay? So when this switch is closed, our circuit is therefore complete, and therefore there's going to be a current produced, okay? And this is a change in current because our current before was 0, and now our current is trying to get to a max value, okay? Now the key word there is trying, because our rate of change of current is at a max, and therefore our back EMF is at a max, okay? And so at this instant, our inductor is going to be producing its greatest EMF that opposes the oncoming current, okay? And just like our circuits with capacitors, this circuit also has a time constant. And our time constant is equal to our inductance all over our resistance. And so therefore in this circuit, our inductance is 0.6 henries all over 2.4 ohms, and this gives a time constant of 0.25 seconds, okay? And so just like for our capacitors, we can create graphs for our voltage and current, okay? So this is our current, and we can plot this current against time. And so if we think about this, when we flip the switch, initially there's going to be a back EMF being produced, okay? So this back EMF opposes our supply EMF, okay? And so we can imagine at this point, the current is going to be 0, okay? However, as time goes on, this back EMF is going to decay as such, and so therefore it's eventually going to become non-existent. And so at that point, when it's non-existent, the current is going to be max, okay? And so we can make a graph like so, okay? So it starts off basically at 0, but then over time it goes to max, okay? And in this case, we can actually calculate our Imax, okay? Because we know that at max current, our inductor sort of acts like an ideal wire. And so therefore our Imax is just V all over R, and we get 12 all over 2.4, and this gives 5 amps, okay? And so we can say that this value right here is 5 amps. Also, we have our time constant of 0.25 seconds, okay? So we have 0.25 seconds, okay? And so therefore we can say that after 0.25 seconds, we reach 63% of Imax, okay? And so 63% of 5 is 3.15 amps, okay? As for our voltage, again, we have our graph where we have time and voltage, okay? Our voltage of our inductor initially is going to be max. So this is our back EMF. Initially, our back EMF is going to be the greatest, okay? Because that's when our rate of change of current is the greatest. And so therefore, we're going to start off with a max value. However, as time goes on, that back EMF is going to decay almost to 0, okay? So it's almost going to be non-existent, and that's why we have our max current being produced. And so what that's going to look like is we're going to have a max voltage, and that's going to decay all the way to basically 0, okay? And again, after one time constant of 0.25 seconds, we're going to reach 37% of our Vmax value, okay? Now, obviously, this graph is definitely not to scale because this is definitely not 37%, but you get the idea, okay? and our initial max voltage is going to be equal to the voltage of the supply, okay? So the back EMF being produced is going to be equal to the supply EMF, okay? And so therefore, we can say that's 12 volts for our Vmax, okay? And so therefore, our voltage after one time constant is 4.44 volts, okay? Okay, so that's what happens when we close the switch. However, if we have closed the switch and then we decide to open the switch again, what happens in that case? So this is the case when we're disconnecting. So to explain this, I'm going to draw another circuit, okay? It's going to be similar, but there's going to be one extra component. So we're going to have our power supply right here, and we're going to have a switch in our inductor with an iron core. And then we're going to have a resistor over here. And in parallel, we're going to have a light bulb, okay? Now let's keep all this the same. Let's say this is 0.6 henries, 2.4 ohms, and this is 12 volts. And let's say this bulb has 7 ohms of resistance, okay? All right, so as you can see, this lamp doesn't really change much of the circuit. It's more for illustration purposes, which I will explain later. Because if we were to connect the switch like we have over here, this bulb is just going to be fed 12 volts, and then due to P is equal to V squared all over R, it's just going to glow, okay? It's going to have a brightness. So when we disconnect our switch, okay, so when we open our switch, if we remember back to our properties of inductance and Lenz's law, we know that our inductor creates an EMF that opposes the change in current, okay? And we can see that through this equation, okay? Creates an EMF that opposes the change in current, okay? And so when we disconnect the switch, the current wants to go to zero, right? Because our circuit is now disconnected from the power supply. However, our inductor wants to resist that change, okay? So wants to resist the circuit's desire to have zero current, okay? And so the inductor wants the current to continuously flow, okay? So that's the opposite of what happens over here. Over here, the inductor prevented the current from rising after a certain time. However, in this scenario, the inductor is preventing the current from going to zero, okay? So the inductor is going to produce an EMF such that the current continues to flow. Okay, and this EMF is now going to push the current in this loop right here. Okay, and this is because this side of the circuit is now disconnected due to this switch. Okay, so now we just have a series circuit with a resistor and a light bulb, and our inductor is now our supply or our source of EMF. So the inductor wants the current to continue to move at I max. Okay, we established that before, and we already established in our previous circuit that our max current is 5 amps, okay? So our current is 5 amps, and the total resistance in the circuit is now going to be 2.4 plus 7, and that's equal to 9.4 ohms, okay? So now we can use Ohm's law, V is equal to IR, to find the voltage or the EMF being produced by our inductor. So we have our current of 5 amps times our resistance of 9.4 ohms, and this gives a voltage of 47 volts, okay? So right off the bat, you can see this 47 volts being produced by our inductor is much, much greater than the power supply's EMF, okay? So that just shows us that the EMF that is produced by an inductor when you unhook the inductor from the rest of the circuit can be incredibly large, okay? In our previous example, this EMF was only limited to 12 volts, okay? It only produced a back EMF such that it would oppose the oncoming current. However, over here, this EMF realistically has no upper bound, and we'll get into that later. Okay, but just like in this scenario, this EMF does not last forever, and so what we can say is that this bulb, which is initially going to be glowing pretty bright, okay, because our voltage is massive, this bulb is eventually going to fade and no longer be glowing, okay? But we have a new time constant now, okay, because we know our time constant is our inductance all over our resistance, and our resistance value has now changed. From previously, our previous resistance value was 2.4, okay? So we're going to have a new time constant, 0.6 all over 9.4, and this gives a value of 0.064 seconds, okay? So if we were to graph this like we did previously, we'll have our current over here, where we have our I, and this is over time. Obviously, like I said previously, when the switch is first opened, the inductor wants to resist the change of making the current go to zero, and so therefore it's going to try to keep the current at max. And so initially, the current is max. However, because we know the inductor is only a limited source of EMF, it doesn't produce an infinite EMF, this current is going to drop in an exponential decay, And once more, we're going to have our time constant of 0.064 seconds. And this is the time it takes for the current to drop to 37% of Imax, okay? And remember, Imax was 5 amps. As for our voltage, V over here, time over here, it's a similar situation that we have for our current. Initially, the EMF produced by the inductor is going to be the greatest, and therefore, because the inductor cannot sustain this EMF, it's eventually going to decay to 0, okay? And so we're going to have Vmax, and it's going to decay to 0 like so, okay? However, remember, Vmax in this case is not the voltage of the supply. It is, in this case, 47 volts, okay? And once more, we have our time constant of 0.064 seconds. And this is the time it takes to go to 37% of Vmax, okay? So as I stated previously, our Vmax in this case is much larger than our supply, okay? Remember, in the previous case, our Vmax was limited to whatever the supply was, as 12 volts, okay? But in this case, it's much, much larger. And the reason for that, you can see, is our resistance. Our resistance is much larger, okay? Remember that we're capped at the exact same current value, okay? Because the inductor only wants to keep the same current value. It will resist changing it in any way, and that includes making it higher, okay? So it will keep whatever the current value is, and so therefore, because V is equal to IR, if our I stays the same but our resistance increases, then our voltage will increase, okay? So the reason for our voltage increasing is because of the increased resistance. And so therefore, if we were to change this light bulb to a resistor, and let's say this is 500 kilo ohms, okay, instead, if we were to now change this 7 ohms will be replaced by 500 times 10 to the 3, and that's going to equal this absurd value right here, okay, and therefore we're going to replace this as well, okay, and this gives a voltage value of 2.5 million, roughly, okay, 2.5 million volts. Now that is extremely large, okay? And so as you can see here, we can artificially make this voltage that is produced by this inductor as large as we want. We can make this like 1,000 kilo ohms, okay? We can just make this a crazy, crazy, crazy value to make this voltage as big as possible, okay? So now, if we were to now, rather than putting a resistor here, we just leave it as empty space. So now, theoretically speaking, this is now infinite resistance right here, okay? Infinite resistance. If we have infinite resistance and we times that by a current value, we are going to theoretically have infinite voltage. Now in reality, we don't actually have infinite voltage, okay? The reason for that is because we don't have a vacuum here. This is still air, and air can still conduct electricity, even though it's a poor conductor of electricity, it still can conduct electricity. That's how we have lightning, okay? And just like lightning, a similar scenario is going to happen over here. If we have this theoretical infinite resistance, our voltage value is going to be absurdly large, and therefore we're going to create a spark across here, okay? A spark. And we see this all the time in real applications when we want to generate a spark. This is something like a car. Inside a car engine, we ignite the fuel by using what's called a spark plug, and that has an inductor inside, and every time we want to generate a spark, we just disconnect an inductor, create a huge EMF, and therefore a spark is created, okay? And these types of questions do come up in NCEA quite a bit, and so because it comes up quite a lot in NCEA, you need to know how to explain it. When our resistance value is absurdly large, in this case, we have done a theoretical infinity, okay? But in reality, you can just say that our resistance value is much, much, much larger, okay? When our resistance value is larger, therefore our time constant is going to be very, very, very small. And when I mean very small, we're approximating to 0, okay? So we're almost at 0. And this is because we are practically at infinite resistance, okay? And so if we relate this to our inductance equation for the EMF that is induced, we can see that this equation is related to the time constant, okay? And so if this time constant is practically 0, we can see that this value right here is going to jump up extremely, extremely high, okay? And that's how you would explain it in a question in an exam, okay? And so that will be it for inductance. See you.